Okay, so welcome everybody. It's my pleasure to introduce Nuutti Hyvönen. Nuutti received his PhD in 2004 at Helsinki University of Technology under the supervision of Erkki Salmersalo. He was working as an Academy Research Fellow for the Academy of Finland through the years 2010 to 12. After that, he became an associate professor in applied mathematics at Aalto University in 2012. And now he is serving as the head of the Department of Mathematics and Systems Analysis since 2018 as a full professor. Thank you, Nuutti, for your talk today. I'll let you take it from here.
Thank you. Thank you for the invitation and the introduction. So it's nice to give this kind of talk, although it would be sort of also nice to get to visit some conferences and meet people in person at some point, but hopefully that will happen rather sooner than later. So really my talk is about monotonicity method for extreme singular and degenerate inclusions in electrical impedance tomography. And to begin with, I might say a couple of words about what I mean by extreme, singular, and degenerate. So by extreme, I mean inclusions that are either ideally conducting or insulating. Then singular means that the conductivity might go to infinity somewhere within the inclusion, and degenerate means that the conductivity may go to zero in some parts of the inclusion. So these are kind of extreme cases, and of course these kind of things, at least for extreme inclusions, they have been considered already previously. Maybe the parts about degenerate and singular inclusions are slightly newer in general. Anyways, for the monotonicity method, these extreme inclusions that are either ideally conducting or insulating, they haven't been really considered before this work. And I should also say that this is joint work with Valentina Candiani, who's working as a postdoc in Genoa. She used to be my doctoral candidate or graduate student here at Aalto University. Then the other collaborators are Jeremy Darde from Toulouse and Henrik Garde from Aarhus in Denmark. And just a few words about electrical impedance tomography. It's kind of the standard inverse elliptic boundary value problem that everybody considers, or many people, maybe too many people consider in inverse problems. Anyways, it's a nice model problem where you can test many things, and it also works in practice to a certain extent. So the idea is that you try to figure out what's the interior electrical conductivity of some physical object by carrying out measurements of current and voltage on its boundary. So here there are a couple of examples that have been computed with a different method for imaging of the human head. So these are not really not really imaging of human head, because these are a bit simulated data and excluding the skull from the consideration. But anyways, you can see on the left-hand side that there's some object with homogeneous boundary conductivity, and then there is certain conductive inclusion inside the object. And typically when you see reconstructions by EIT, these are probably a little bit worse than the typical reconstructions, but you can see some hotspots at the locations where the inclusions are on the left-hand side. So this is actually sort of an example that I will consider today. I won't present any numerical examples, but the idea is really not to consider the general task of reconstructing the conductivity inside an object, but to characterize inclusions inside the object. So the idea is to find the support of a conductivity inhomogeneity inside an object with known background conductivity. And with that being said, the method that I will use is something that could be used also with simulated measurements, and also it has been used for reconstructing inclusions in electrical impedance tomography with actual water tank measurements at least. So it's a functional method, and it has been proven to be able to reconstruct inclusions in electrical impedance tomography, both positive, meaning more conductive inclusions than the background, and negative inclusions, also indefinite inclusions where the conductivity may be both positive or negative compared to the background. And this work has been carried out by Harra and Ulrich and their collaborators and other people already like 10 years ago. The thing that we tackled 2 years ago approximately is to include in this consideration perfectly conducting and insulating inclusions. These weren't considered previously. So the idea is that the inclusions that I consider, they may be perfectly conducting, perfectly insulating, or there may be some combination of these two and also finite perturbations of the background conductivity. So by inclusion, I mean something really general. So it's something that varies from the background in rather arbitrary manner. And in addition to this kind of extreme, please, there's a question, I guess. Or is there? Okay, so.
Yeah, there is one. It's our usual thing to take questions at the end, but as long as we're doing this, I'm not quite sure. I'm trying to unmute Brigitte. Oh, okay, yeah. I think for technical reasons, it's best to take the questions at the end, because I'm not sure if I have the mute or the unmute power.
Okay, yeah. So maybe I will continue, and I will then try to answer the questions at the end. So sort of also regarding this introductory part.
Yeah, thanks everyone.
Yeah, thank you. So anyways, here the inclusion kind of should be understood in the sense, I will give a slightly more precise definition, but the idea is that you, for example, know that the background conductivity of the object should be 1 in some sort of some unit, some mathematician's unit. The conductivity is 1, and then there's some perturbation of the conductivity that is compactly supported inside the object, and the task is to give a mathematical characterization of that support of that inclusion. And really the sort of new part are the allowing with this monotonicity method, perfectly conducting or insulating inclusions, as well as this kind of this kind of A2 Muckenhaupt weights that may go either to infinity in certain controlled manner, or they may go to 0 in certain controlled manner. And then about the outline of the talk. So first I will introduce the continuum model that I will be using. So in order to be able to prove actual some reconstruction results, one needs to typically use continuum model. So there are also new results on uniqueness for finite parameterizations of the conductivity using only a finite number of measurements, but that's not something that will be considered today. So I will assume that I have this kind of idealized measurements, infinite data kind of, and then I will introduce the monotonicity method and then consider characterization of inclusions. And the final part is just noting how the singular and degenerate inclusions can be tackled. This second part here might seem a little bit odd, but the idea is that part of the technique that we use for tackling the detection of the extreme inclusions is to know how the Neumann-Dirichlet boundary map, that's how we model the boundary measurements, how that converges when you let the conductivity level inside certain inclusions go to 0 or infinity. So we prove that the boundary map converges towards the setting where you actually have inclusions that are either ideally conducting or ideally insulating. So at the limit, you can replace the conductivity, either really small or really large conductivity inside an inclusion by either homogeneous Dirichlet or Neumann boundary condition on the boundary of the inclusion. So I will start with the continuum model, and I will introduce it so that it actually takes into account the extreme inclusions to begin with. So here's kind of the continuum model with extreme inclusions. So I consider some bounded domain with Lipschitz boundary omega in 2 or higher dimensions, so no restrictions on the dimension, and I assume that the object has a connected complement, so kind of standard assumptions. Then I will consider only partial measurements, so there's some open non-empty subset of the boundary where I assume that I can carry out the measurements. So the theory works on, in principle, it works for any open non-empty subset of the boundary. Of course, you may assume that everything is more stable if you have a large portion of the boundary where you carry out the measurements. In this to begin with, I assume that there are both insulating inclusions inside the object or inhomogeneities and ideally conducting inhomogeneities. And this C denotes the union of those two, and always when I have naught 0 as a sub-index, that means that that region corresponds to insulating inclusion, and infinity means ideally conducting inclusion. And I need to make some assumptions about the geometry of these objects. The things that I assume to begin with, or this kind of, how should I say, playing assumptions that make everything safe, is that the two inclusions are closures of open sets with finitely many components and Lipschitz boundaries, and they should be disjoint. So this means that actually they have some distance between them because they are closures of open sets. And then the complement of the insulating inclusion needs to be connected. However, for the forward program to work in the way that I will present it on the next slide, these are sort of too heavy assumptions, because you can see that the variational formulation that I keep works for more general geometries. So you don't need to, for example, assume that the two regions don't touch each other and so on. The Lipschitz boundary, the condition that we assume Lipschitz boundaries, that's a technical assumption, as well as this fact that we assume that there are finite many components. So those are related to the way that we have carried out the analysis. So straightforwardly, I don't know how to get rid of those, but in intuitive sense, those shouldn't be any restrictions either. Okay, but anyway, C naught is insulating inclusion, C infinity is perfectly conducting inclusion. Then I use a zero mean boundary density on the boundary portion gamma. So this bracket thing denotes L2 inner product on the boundary part gamma, always during this talk. And of course, this needs to be zero mean this current pattern in order for all current that flows into the object must also come out. And I'm considering L2 current patterns on the boundary portion gamma. And then I assume there's some background conductivity. It's this plus sign means that the conductivities in this L infinity plus space, they have a positive infimum. So positive conductivity, it can be L infinity conductivity. And then I denote by sigma this kind of generalized conductivity coefficient. So when I write sigma, var sigma, C naught, C infinity, it means that I'm kind of considering conductivity that is this var sigma in the complement of the inclusions. Then it's zero inside the insulating inclusion and infinity inside the ideally conducting inclusion. Of course, you need to understand these in the proper sense, but intuitively you should think about, when you see this kind of notation, you should think about conductivity var sigma in the background, and then two inclusions, C naught and C infinity, that are insulating and ideally conducting respectively. And now I formulate the forward problem. So the intuitive idea, or the PDE formulation of the problem, is that I have the conductivity equation with no source term in the region where inside omega, where there are no insulating or ideally conducting inclusions. Then the boundary current density is zero on the part of the boundary where I don't control the current, plus on the boundary of the insulating inclusion. And then on the boundary portion where I can control the current, there I have some F as input. So this is the boundary current that I'm actually controlling. And the other parts, on the other parts, the boundary current is zero due to the insulating property of C naught, or the fact that I assume to not be able to control the boundary current on in the complement of gamma in the exterior boundary. And then I model the ideally conducting inclusions with the property that the gradient of U should be 0 in the interior that was open, of course, but I defined C infinity as closer of an open set. So this is kind of, there's no ambiguity about this notation over here. And I just say that U should have 0 gradient over there. So in the ideally conducting part, there should be no potential differences. And now by defining this kind of new function space, probably used somewhere else previously, but anyways, kind of non-standard, which is H1 Sobolev functions in the exterior of the insulating inclusion, plus this kind of condition that the mean of these functions should be 0 over this gamma part, the part where I'm controlling the currents. That's just the grounding of the potential, so it's not really essential. But there's another thing that I'm considering H1 functions in the exterior of the insulating inclusion, and I'm sort of imposing the condition that the gradient of any function or in this space should be 0 in the interior of the ideally conducting inclusion. So this kind of mimics the idea that when you do variational formulations of PDEs, then the sort of Dirichlet boundary conditions, such as you could interpret this one, because it says that the potential is constant inside the ideally conducting inclusion. It's included in the definition of the variational space, whereas the Neumann boundary condition is in the sort of included in the actual variational equation. So now, after defining this kind of space that already takes into account the ideally conducting inclusion, then I can formulate the variational problem corresponding to this boundary value problem in the way that I say that this standard sort of sesquilinear form for the solution, it's satisfied in the exterior of the insulating inclusion, and then this should equal the sort of F, the imposed boundary current density times the test function. And this looks really familiar. So if I didn't have any ideally conducting inclusion, this would be the standard variational formulation. But now the trick is that I'm looking for the solution in this space that already takes into account the ideally conducting inclusions, and also the B, the test function over here, lives in that space. So you can quite easily prove that these are equivalent if you interpret the boundary conditions over here in the correct sense of traces. And furthermore, if you recall how I defined these, sort of I had this kind of requirements on the inclusions that they are sort of, they don't touch, and omega minus and also that they lie well within the domain because they are closed sets that are inside omega. I could actually get rid of those, at least some of those, because this variational formulation can be formulated for much more general inclusions. But however, I won't go into those details. This is anyways what I sort of mean when I say that I'm solving the forward problem. I'm looking for U that satisfies U F sigma that satisfies this equation for all B in this new variational space. Finally, I should say that this space actually plays a relevant role. It won't be sort of explicitly mentioned, but many parts of my analysis. So for example, there are certain constants that I will introduce that depend on, let's say, on the projection of certain function from this space onto this subspace and so on. So this is actually kind of a relevant tool in what follows. Also, one thing to note is that this equation wouldn't change if I replace this C naught by C, because these functions, these gradients vanish inside C infinity, which means that I could have as well formulated this without this, with C replacing C naught over here. Okay, so that's the variational formulation, how I understand the forward problem with this kind of extreme inclusions. And then about the inverse problem. So all of us probably know about the inverse problem of electrical impedance tomography under idealized boundary conditions. So the idea is that you define the current to voltage map. Okay, sorry about this notation. So I have learned to use lambda as the Neumann-Rillet map. So many of you probably used for the Rillet-Neumann map, but for me, it's always the Neumann-Rillet map. And in this case, it's the sort of restricted Neumann-Rillet map. So it takes L2 mean-free L2 functions on gamma and maps them on mean-free L2 functions on gamma. This mean-free condition is due to physics. This is by choosing the ground level of potential appropriately. It's a compact map because I could also use this kind of fancy h-half and h+half spaces over here, but this is enough for my purposes. And the forward map for electrical impedance tomography, or its idealized version, is the mapping from sigma. That is, here I have quotation marks because I also include these extreme inclusions in the equation, but in the standard setting, you would say that you are looking at conductivity that is positive and in infinity, and the forward map takes that onto the Neumann-Rillet map that is a bounded linear operator, even compact, from L2 diamond on gamma to itself. And the inverse problem is to reconstruct sigma from the knowledge of this lambda. However, I won't consider this general reconstruction or uniqueness problem, but I'm only interested in inclusion detection, as I have mentioned. So I would like to be able to locate conductivity perturbations that may be sort of extreme or even Muckenhaut weights from a known background. And by trying to list methods for this task, I would do disservice for many people because by listing some, I would forget to list others. So there are many methods for inclusion detection in EIT. So I decided to not list any because I would anyways probably not list tens of methods if I try to have some comprehensive list. So this isn't the first method. I'm not claiming that this is the best method, but at least I find it interesting due to certain sort of physical interpretations. So next, about convergence of the Neumann-Rillet map. And I will state it as a theorem without a proof. So this is not really surprising, but we couldn't find it, at least not easily from anywhere. So the idea is that if you have this kind of conductivity coefficient that is characterized by this background conductivity and two inclusions, one ideally conducting and one ideally insulating, then you can define this kind of epsilon truncated version of sigma, where you have in the exterior of the inclusions, you have the background conductivity, and in inclusions, you scale the background conductivity that is defined everywhere inside the object by epsilon or epsilon to the power -1. And now, of course, this goes to 0. When epsilon goes to 0, this goes to infinity. And you can actually prove that the corresponding forward solutions converge to each other, the one with inclusions and the one with this kind of truncated conductivity, and they converge in the exterior of the insulating inclusion. So inside the insulating inclusion, actually the speed of convergence or sort of dictates where you converge. So that's a different interesting phenomenon. But anyways, you know that these converge, and you actually have this kind of nice estimate that you know that there's some constant that is depends only on the geometry. Then you know that the speed is at least epsilon to the power 1/2, and then you have the norm of the current pattern. And now by taking trace, you easily see that also, and because you have the norm of F nicely over here, you see that you have also convergence of the Neumann-Rillet maps. So now many of the things that I would need to do for this operator, I can actually do for truncated operators. This kind of solves half of the problem with the monotonicity method and extreme inclusions. Anyways, that's just a theorem. We know that those mappings converge nicely. And then let's move on to monotonicity method for extreme inclusions. So the thing that I personally really like about this monotonicity method is that it's based on something that is easily, sort of 1/2 of it is based on something that is really easily understandable physically. So it's written mathematically over here. So I have two Neumann-Rillet maps that are actually restricted Neumann-Rillet maps, but that doesn't really play a role. I operate with the difference on some boundary current pattern, take the inner product with the same counter current pattern, this should be some kind of difference in energy. And you can actually see that, so this has been proven by many people many years ago. Once again, it's nowadays generally known, but it's anyway sort of something that is still nice to review. So you can see that if sigma 1 is larger than sigma 2, then this left-hand side here is positive because you are subtracting these two sigmas in different order. And then you have something positive, the squared norm of the gradient of the potential corresponding to F and this conductivity. And on the other hand, the other side, the upper limit or estimate is also really simple, even simpler than the other one. And you can see that that's also controlled by the difference between two conductivities. So how you can interpret this relation is that if one of the conductivities is larger than the other almost everywhere, then you have inverse order in the sense of positive definiteness for the two nomenclature maps. And physically, it's easy to understand what's going on over here. If you increase the conductivity, the power that you need for maintaining current pattern on the boundary can be decreased. And that's why the sort of the operators in the sense of positive definiteness move into the opposite direction. For direct to Neumann maps, this would be the other way around. But for nomenclature maps, smaller conductivity implies larger Neumann-Turlet map. And everything in the monotonicity method is kind of based on this kind of monotonicity relations. And now if you think about moving on to extreme inclusions where the conductivity is 0 or infinity, or even this kind of degenerate or singular inclusions where you allow singularities and conductivities to go to 0 kind of smoothly, then there seems to be nothing that should break down, because still if you have lower conductivity, you should have larger operators on the boundary. Okay, in the following theorem, I need this kind of concept of admissible test inclusions. So A belongs to this set of admissible test inclusions if it's a closure of an open set and has a connected complement and has a Lipschitz boundary. So I'm not trying to find holes inside inclusions. So if there's kind of a hole inside an inclusion, I'm not trying to detect that. I'm just trying to detect exterior boundaries of this kind of conductivity perturbations. So with this in mind, let's move to reconstructing just either ideally conducting or ideally insulating inclusions. So in order to understand these theorems, by the way, there's typo, so that T is extra. So in order to understand these two theorems, this notation should be first reviewed. So by lambda naught C, I mean the nomenclature map corresponding to background conductivity gamma 0 and ideally insulating inclusion C. So this naught tells you that you have the background conductivity and ideally, or especially you have the ideally insulating inclusion C. Then lambda infinity is the other way around. So you still have the background conductivity, but C plays the role of ideally conducting inclusion. And now the two theorems, one is sort of more easily understandable, the other is more sort of numerically more easy to implement. So they kind of characterize the inclusion D. So D is an admissible inclusion satisfying the conditions on the previous slide. Let's say that D is to begin with an insulating inclusion. And then I ask the question, does some test inclusion, let's say it could be a test ball, belong to D? And the result is that it belongs to this to be located inclusion if and only if this condition holds. So what I do over here is that I have the inclusion D in the background, it's insulating inclusion, and then I compare it to the background conductivity minus some positive number times the characteristic function of B, and this positive number is chosen so that the conductivity stays positive. So from the monotonicity principle, it's easy to understand that this holds, this only if part holds, because if B is included in D, then I directly have the monotonicity by taking the limit in the theorem that I considered. The other way around is more difficult, and proving it for the ideal, this extreme inclusions is also more difficult than the other case. But anyways, it gives, you can then test different P inclusions, and if and only if this holds, then you know that this P belongs to the to be located inclusion. And by trying enough test inclusions, you can reconstruct D up to, of course, the instability of the inverse problem. And then for ideally conducting inclusion, if you want to know that there's an ideally conducting inclusion, then you can once again take test inclusions, and you have an if and only if relationship. But this time around, because the ideally conducting inclusion is the most sort of energy-wise the smallest inclusion for the normal-related map, you have that this test normal-related map should be larger or equal to the normal-related map corresponding to the ideally conducting inclusion in case this B is inside D, which is the to be located inclusion. But I have also the if condition over here. So also if this doesn't hold, then at least theoretically this can't hold. I won't probably go into the details of the latter theorem. The idea of the latter theorem is that by sort of having a little bit stricter condition on this B beta parameter, I can also do this linearization. So I can replace these test normal-related maps by linearized versions. So I don't subtract beta inside the argument of lambda, but I multiply by that the corresponding Frese derivative, and still I have if and only if conditions. And these are numerically easier to implement because I only need to compute the, this derivative for one conductivity, not for multiple conductivities. But these ideas for non-ideally conducting or insulating inclusions, they were introduced already by Harra and Ulrich, so that's not new. So what is new is that we can do this also for ideally conducting or ideally insulating inclusions. And then due to time restrictions, I will just sort of briefly say about how these proofs work. So the only if part is easy, so you just use the standard monotonicity principle for truncated conductivities and then pass to the limit. Then the other way around, so meaning that if actually these don't hold, then you don't. Okay, let's see. So the difficult part is to show that this can't be, let's say this can't be larger than that if beta is at least slightly larger than D. So that's the more difficult part, and also sort of less intuitive part that can be tackled by the theory of localized potentials by Harra. They are, you could say that they are related to also Runge approximations for this kind of, the idea is to concentrate the energy in the current that you are inputting in the region into the part where the other conductivity, the test conductivity, is either larger or smaller than the inclusion that you are trying to locate. In principle, the theory of localized potentials works over here for the other direction, but you need more case-specific monotonicity estimates. And these are kind of the kind of estimates that you need. So if you have the same inclusions for the two normal-related maps, but you have different conductivities, then the estimates, monotonicity estimates, are exactly the same. Then if you have the same background conductivities, but you have either an ideally conducting inclusion or no ideally conducting inclusion, then you know that this should be smaller than that because there's something ideally conducting inside. And then you can write this kind of estimates that really something, you take some gradient multiplied by something inside C infinity, and that provides both a lower bound and an upper bound. The lower bound is kind of explicit. This upper bound depends on K, which is a constant that is related to the projection that I mentioned previously, but it's independent of F. And then if you have the same conductivity for the two normal-related maps, but either insulating or no insulating inclusions, then you know that this should be larger than that in the sense of positive definiteness. And once again, you can write an explicit lower bound where you have the solution without the ideal insulating inclusion, and the upper bound is a little bit more abstract. So this object here doesn't actually live inside C naught, but if you extend it as a solution of Dirichlet problem so that it's still in H1, then this holds. So this is probably the most technical parts of our work, and but I won't go into details about how to prove them. But this kind of also sort of they were used to prove this kind of detection of ideally conducting or ideally insulating inclusions, but we can do much more with these estimates. So let's consider rather general indefinite inclusion. So D is now the inclusions that I'm trying to locate. It's composed of a positive part that is more conductive than the background and a negative part that is less conductive than the background. Furthermore, the less conductive part is composed of an ideal insulating inclusion and a finite inclusion that is less conductive than the background. And then the other way around, I have the plus part, the more conductive inclusion that has a positive part that is finite, and then an ideally conducting part. And then I define the whole conductivity for which I'm trying to locate D, so that the conductivity is 0 in D0, infinity in D infinity, and then I have some finite point perturbations in these D finites, and then I have the background conductivity. These different inclusions need to satisfy certain geometric conditions, so still I'm not letting D naught and D infinity touch each other. Furthermore, in the paper, we assume that the conductivities inside these finite inclusions are positive, strictly positive, or strictly negative, depending whether it's less conductive or more conductive. But you can actually relax this assumption because it's enough to be able to concentrate the energy in certain part of the inclusion. So it's enough that you can connect the boundary of the domain to certain part of the inclusion where the conductivity is either larger or smaller than the background in some subset of that region. So there would be it would take lots of time to consider what kind of inclusions you can't actually tackle, but you can think about some infinite oscillations. Those are difficult. So infinitely fast oscillations, then it's difficult to concentrate the energy to a certain part of the inclusion where that is connected to the boundary by an open set. But anyways, the intuitive idea is that I have some inhomogeneity that is both positive and negative compared to the background, and there are also ideally conducting and ideally insulating and ideally conducting parts in the inclusions. And here's the sort of not necessarily numerically so easily implementable result, but it's rather compact, I would say. So let's say that C is now my test inclusion, and it corresponds to, in this case, it corresponds to an ideal insulating inclusion because I have lambda naught over here. In this case, it corresponds to ideally conducting inclusion because I had infinity mark over there. So these are kind of extreme Neumann-related maps in the sense that this is as small as possible Neumann-related map if this C has a sort of certain conductivity between infinity and 0, because it has infinite conductivity inside C. This is kind of as large Neumann-related map as possible for inclusion C because it has insulating inclusion C. So if I know that the perturbation of the conductivity is within C, this is as large Neumann-related map as I can get. This is a small Neumann-related map as I can get. And now the result is that if I have this kind of admissible inclusion, so it's compactly supported inside the domain, there are geometrical properties, quite a few of them that needs to be satisfied. But the idea is that, okay, C is the test inclusion, but D is the inclusion defined by these conditions. There are more conditions, but I won't go into details, so how these should interact, these different sets. But the idea is that if I ask the question whether C, my test inclusion, contains D, then it happens if and only if these two Neumann-related maps give upper bound and lower bound for the Neumann-related map that I can measure. So the fact that these hold if D is included inside C, that's intuitive due to the sort of consumption of the energy. The less intuitive part is that it also holds the other way around. So if this isn't satisfied, then I can concentrate the energy in the part of D that sticks out of this test inclusion and find one of these two inequalities fails in the sense of positive definiteness, because I can kind of catch the small part of D that sticks out of C and concentrate my energy over there. Of course, I can't concentrate the energy, all of it over there, but I can kind of have a path for energy so that it's the highest by the boundary of the whole domain, and then it kind of goes towards the part that sticks out of C if D extends outside C. And then in particular, I can reconstruct the whole inhomogeneity that is kind of complicated by taking all C's for which this holds. And still, this is at least one of the two directions is kind of intuitive, because I'm just sort of saying that I'm taking the most largest possible nomenclature map for that inclusion and smallest possible, and I'm checking out whether the actual measured inclusion is between those two. Okay, and then last 5 minutes about sort of going to singular and degenerate inclusions. So still, if you think about this, so even if this gamma has something that goes to 0 or infinity, kind of the monotonicity, one would assume that it might still hold. So it's more about defining the nomenclature map for a case where you let gamma have singularities or parts where it goes to 0. So really I can update my inclusions so that I don't have only sort of finite negative parts, 0 parts, but I can have also degenerate parts where this the conductivity in the degenerate part is such that it may go to 0. So it can be an A2 Muckenhaupt weight inside the degenerate part of the inclusion, this conductivity. And also the positive part has also this kind of singular part, and inside this singular part, the conductivity can be A2 Muckenhaupt weight that may have a singularity that goes to infinity. So both this kind of smooth or continuous approach of infinity and 0 are allowed in the respective inclusions. And there are further geometric inclusions, conditions, most importantly, that the 0 sets and singularities of these degenerate and singular parts must lie within the interior of these. So at least we weren't able to prove it in the case where you kind of start with the singularity in your conductivity. So, or kind of the inclusion starts with something being 0. So the singularities need to be in the interior of the inclusion or inhomogeneity. And then proof in a nutshell. So I haven't really proven anything, but this use of A2 Muckenhaupt weights is kind of standard. That's how you can extend elliptic equations. So if this condition is satisfied by the conductivity, then there's standard theory of proving the uniqueness of the forward problem with using weighted Sobolev spaces. And then the claimed generalization follows. You can't probably see it easily, but you just need to prove that if you have this conductivity where you have these degenerates and singular parts, then if you replace both the degenerates and singular part either by 0 or infinity, then the monotonicity holds. So that's intuitively, once again, sort of understandable, because if you replace something that might be positive with 0, you should have something that is larger in the sense of nomenclature maps or positive definiteness. And if you replace something that is positive by infinity, then you should go to the other direction. And these can be pretty neatly proven using sort of the variational analysis of the forward problems. So they minimize certain functionals and so on. And by doing these tricks, you can see that this holds. And that pretty much sort of concludes the proof, although it's probably not possible to see it here. Finally, what kind of degenerate behavior or singular behavior one can have. So if you take a point inside the inclusion D, then these degenerate and singular parts may go to infinity 0 or infinity with certain speed that is dimension dependent. You can have, if you have some let's say Lipschitz hypersurface, you may have this kind of behavior that the conductivity goes to 0 or infinity with a lower speed. In particular, what can happen is that with the control speed, the conductivity that you're looking at may go to 0 when approaching the ideally insulating part and may go to infinity when approaching the ideally conducting part. So it's possible to consider inclusions where you kind of have an insulating inclusion and then you go to 0 smoothly with a control speed when you approach that inclusion. And finally, conclusion, although this is really well organized seminar series, and it's nice to give talks here also. It would be really nice, as I mentioned to begin with, to actually get to actual conferences and work with physical people. So this is actually with Valentina, who's now postdoc in Genova. We were working out, sort of trying to figure out how these nomenclature maps converge in Valencia in the SIAM conference a couple of years ago. So this is a napkin, and there's really clever analysis on the napkin. And finally, a couple of, as I said, I'm missing lots and lots of references that I should list, but these are the ones that are sort of make the presentation understandable if you look at this. So first of all, this kind of monotonicity ideas were introduced by Tamburino and Rubinacci already some time ago. Then Bastian Gebauer, meaning Bastian Harrach, he introduced these localized potentials in 2008. Then the monotonicity-based shape reconstructions without these extreme inclusions or Muckenhaupt inclusions, that was already in 2013. And then these are the two papers where you can find things that I talk about here. Thank you.
Thank you, Nuutti. This is fascinating. I see we have a question from George in the audience. Go ahead. Maybe he doesn't know he has his hand raised. Okay, let's try. Are there any questions? Okay.
Maybe could I start with a question just to get things going? Thank you, Nuutti. It was very interesting. You mentioned in the beginning that you needed the inclusions to be ellipses, but could you go along with cusps, for instance, or things like, for instance, where you would have pieces that would be very close from one another?
Yeah, so actually, even when I told that at a certain point we could have sort of this is kind of sort of a condition that makes sure that everything is nice. So even in the case where we let the inclusions touch, at least the way that we have proven everything, we needed to assume that, let's say, omega minus c and omega minus c naught and omega minus c infinity have Lipschitz boundary. So of course that's probably more related to the way that we are sort of comfortable using all Green's formulas and so on. But the thing is that now and then you need to, when you prove this theorem, you kind of go to the boundary of the inclusions and integrate over there. And then it's sort of, it seemed like a safe thing to do, that to assume that everything is Lipschitz, because then we know that everything should work. And also there was a problem that if the inclusions have infinite number of components, then everything gets a little bit complicated. So it's difficult to sort of say whether you are misleading yourself or not. So for that reason, we assume that you have only finite number of components in these extreme inclusions.
I see. Mm-hmm. Okay.
I have a question. So Nuutti, in practice, I'm not quite clear on the practical role of the lambda 0 and the lambda infinity. Would you need to compute those from simulations? Yes, so that's in this case that wouldn't be so difficult because, okay, in this case, when these first two theorems here, the idea is that we know that there's an sort of either insulating or ideally conducting inclusion, so you actually measure it. So in this case, this linearized thing to do is actually pretty efficient, because you only need to know the background conductivity and the corresponding nomenclature map, and then around that background conductivity, you need to numerically approximate the Frese derivative. So you need to compute the Frese derivative, but you don't need to compute, as over here, the whole forward map for all the test inclusions, because B is now the test inclusion. So this can be sort of detection of the extreme inclusions can be done pretty efficiently. However, the thing that wouldn't be so efficient is this part, because here one would like to have some kind of similar linearization approach, but
But here, the unknown inclusion or unknown perturbation is included in this gamma over here. And to test whether C contains the perturbation in gamma, one needs to compute these sort of nomenclature maps, which means that you need to always solve a forward problem corresponding to certain boundary condition on the boundary of C to actually get the sort of test nomenclature map. And the thing that might be interesting to consider, because if you don't have this infinite inclusions, then you can have a linearized version, as far as I know, of this as well. So that's actually sort of something that could be considered, but this isn't really efficient numerically. I would claim that these are pretty efficient to implement, but they are only for detecting these extreme inclusions.
Okay, but if you wanted to detect, for example, a metal inclusion in a person's body, you don't know if it's there or not, you could use the theorem that you have on the screen now. Yes,
so of course there are some sort of difficulties, like if you consider electrode measurements, then the monotonicity works still in one direction. So still, if you know, let's say, the contact impedances, then if you have a less conductive object, you know that the energy should be less than if you have the metallic inclusion, then you could sort of use the other part of the monotonicity result. But the part where you need to concentrate kind of the energy somewhere, you can't do that without having really high oscillations in the boundary current. So the other direction doesn't work as well. But in principle, yes, and I know that Bastian von Harra has implemented this for real measurements and so on. And I guess also for ideally conducting inclusions, although the theory didn't kind of cover it previously. He probably knew that it works, but he hadn't proven it.
Nice, thanks. It looks like Erkki has his hand raised.
Okay, do you hear me?
Yes.
Yes.
Yes. Yeah, so nice talk. Do you think there's anything similar being done with Maxwell's equations, like impedance map? And
yes, actually, I don't know the details, but I know that Roland Griesmeier has recently published work on using this kind of monotonicity principles for Maxwell's equations. So there has been some things for Helmholtz equation. So you kind of need to exclude, when you consider the positivity, you need to exclude certain parts, sort of accept that the monotonicity doesn't work for the kind of for the whole spectrum, but there's a part that needs to be excluded or something like that, because it's not kind of a coercive equation by nature. But for the Maxwell equation result, I don't know the details, but I know that there's a recent publication by Roland Griesmeier and I think his graduate student, if I remember correctly.
okay, thanks.
Great. Are there other questions? Okay, I'm not seeing any other hand raised. Thank you so much, Nuutti, for this interesting talk. I enjoyed it very much. Thank you everyone for attending, and we wish you
Thanks
a wonderful
for having me.
Yeah, thanks.